Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year was 1928. Paul Adrien Maurice Dirac, a name now synonymous with the very fabric of modern physics, presented the world with his enduring treatise, The Principles of Quantum Mechanics. This work, far from a mere textbook, represented a profound synthesis and extension of the nascent quantum theory, etching itself into the pantheon of scientific literature as a cornerstone of our understanding of the universe at its most fundamental level. Its impact reverberates through contemporary physics, shaping not solely our comprehension of the microcosm, but also influencing advancements in fields as diverse as materials science and quantum computing. Before Dirac, quantum mechanics, while displaying impressive predictive power, lacked a unified, coherent theoretical framework. The early pioneers, giants like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, have formulated revolutionary concepts. These concepts included the quantization of energy, wave-particle duality, and the probabilistic nature of quantum phenomena. These pioneers were also exploring the limitations of classical physics in describing atomic behavior. Dirac inherited a fragmented landscape. Heisenberg's matrix mechanics and Schrödinger's wave mechanics, though mathematically equivalent, as demonstrated by Schrödinger himself, initially presented different approaches to understanding the quantum world. Both were complex. Each possessed a unique set of mathematical tools, creating a landscape where physicists grappled with intricate calculations and sometimes, seemingly, contradictory interpretations. Dirac's genius lay in his ability to synthesize these disparate elements, to elevate the principles underlying them, and to forge a new and elegant formula. Dirac's work demonstrated several crucial theoretical advances. Central to Dirac's achievement was his masterful use of a powerful mathematical language. This allowed him to cast quantum mechanics in an abstract, elegant form. Dirac's use of the operator formalism, building upon Heisenberg's matrix mechanics, provided a universal language. Within his formalism, physical observables such as position, momentum, and energy are represented as operators acting on abstract state vectors. These state vectors reside within Hilbert space. This abstract mathematical space provided the framework for describing the possible states of a quantum system. Crucially, this approach eliminated the need for the explicit use either matrices or wave functions, offering a more general and flexible approach. Dirac's bracket notation, a concise and elegant system for representing quantum states and operators, codified this formalism. The notation became a standard language for physicists worldwide. The bracket notation streamlined calculations and clarified the mathematical structure of quantum mechanics. This gave physicists the tools needed to solve problems and interpret results. One of the most striking and consequential contributions of the principles of quantum mechanics was Dirac's relativistic wave equation. For the electron, Dirac sought to reconcile quantum mechanics with special relativity. Previous formulations, such as Schrödinger's equation, did not incorporate special relativistic effects. The equation he developed, now known as the Dirac equation, elegantly combined quantum mechanics and relativity. This equation predicted the existence of antimatter. Specifically, Dirac's equation, when solved, gave solutions corresponding to both positive and negative energy states. Dirac interpreted the negative energy solutions as representing a new form of matter, the positron, an antiparticle, with the same mass as an electron but with a positive charge. Initially, Dirac found this result difficult to interpret. He struggled with the concept of negative energy. The interpretation was then supported experimentally by the discovery of the positron by Carl Anderson. Anderson's discovery validated Dirac's equation. The impact of Dirac's work was immediate and profound. Physicists gained a deeper understanding of the fundamental nature of matter and energy. The applications of his work rapidly grew, leading to new experimental discoveries and technological breakthroughs. The Dirac equation, for example, proved crucial in understanding the behavior of electrons in atoms and molecules. It offered highly accurate predictions of atomic energy levels. Its influence extended to the development of quantum electrodynamics, the theory of light-matter interaction. This became the most successful theory in physics, providing unparalleled accuracy in predicting experimental results. The initial reception of Dirac's work was a mix of awe and some confusion. Some physicists were initially daunted by its mathematical sophistication. Dirac, known for his terse and high-focused approach, did not offer a particularly gentle introduction to the profound implications of his work. Certain aspects, such as the prediction of antimatter, seemed counterintuitive for those steeped in classical physics. However, it became evident, quickly, that Dirac's framework offered a more complete and consistent description of quantum phenomena. The theoretical advances were quickly validated by experiment. Dirac's contributions soon gained widespread acceptance. Researchers recognized that Dirac's ideas were not solely mathematically elegant, they possessed deep predictive power. The work became an indispensable resource for anyone seeking to understand quantum theory. The evolution of quantum mechanics during the years that followed demonstrated the enduring impact of Dirac's ideas. His formalism proved remarkably adaptable and fertile. It served as the crucial basis for many other theories. The Dirac equation has been extended to describe other fundamental particles, like quarks and leptons. Dirac's work played a fundamental role in the development of quantum field theory. Quantum field theory is the theoretical framework upon which the standard model of particle physics rests. The Dirac equation is central to this theory. It describes the dynamics of fundamental particles. It predicts their interactions. The work of several key figures influenced Dirac's thought. Paul Dirac and Wolfgang Pauli introduced the concept of spin. Spin is an intrinsic form of angular momentum for elementary particles. Dirac incorporated spin into his equation. This solved a problem with the previous treatments of the electron. He drew heavily on the operator methods of Heisenberg and the transformation theory of Schrödinger. From these, he developed his own unique and powerful perspective. However, he built upon and improved their formalism. His work did more than merely systematize the work of his predecessors. It unified disparate approaches. It extended those concepts, creating a cohesive theoretical framework. Dirac's rigorous mathematical approach enabled him to solve problems that had confounded other physicists. The influence of Dirac's work extended far beyond theoretical physics. His insights have had practical implications in many fields. The Dirac equation is used in semiconductor physics. It is also an integral part of nuclear physics. In materials science, it is utilized in computational techniques to describe the properties of novel materials. His ideas have inspired generations of scientists. They continue to shape our understanding of the universe. Dirac's influence is readily apparent in quantum information theory and quantum computing. A theory of entanglement, developed from Dirac's theory, offers promising new technological applications. Dirac's principles also fostered new avenues of inquiry. His work spurred ongoing research. Scientists explored the mathematical implications of the Dirac equation, studied particle physics, and explored quantum field theories. His work influenced the search for new particles. The work continues to inspire new experiments exploring a fundamental nature of reality. The exploration of supersymmetry and string theory also owe debt to Dirac's side. The Principles of Quantum Mechanics is a landmark achievement. It presented a synthesis, an extension, and a deeper understanding of quantum theory. Dirac's contributions include the development of bra-ket notation, the operator formalism, and the relativistic wave equation for the electron. This work established a coherent and elegant framework for quantum mechanics. It predicted the existence of antimatter. It helped to create the foundation on which almost all of physics relies. The text's influence is undeniable. The Dirac equation continues to be a fundamental tool. It has had numerous applications. It remains a testament to Dirac's genius and his lasting legacy. It provided a coherent and elegant framework for quantum mechanics, forever altering our view of reality.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.